This lecture is part of a series of lectures for a course entitled The Physics of Diagnostic Radiology. The second lecture, MRI Contrast and Spin Echoes, is broken down into 4 parts. Lecture 2, Part 2, covers NMR Relaxation. At the end of this module, you should reach the following learning objectives: to distinguish between T1 and T2 relaxation, to recall the T1 and T2 for at least 2 tissues, to compare the time course of MZ and MXY magnetization after a 90-degree RF pulse, to recall that short T1s are bright on a T1 weighted image, to recall that long T2s are bright on a T2 weighted image, to appreciate that T2 star decay combines reversible and irreversible spin dephasing. So first, T1 and T2 relaxation. This was previously addressed with regards to the Bloch equations and the consequences of the Bloch equations during free precession periods of magnetic relaxation after, for example, RF pulses in the previous lecture. So here's an example of soft tissue contrast, and we recall that MRI has exceptionally flexible image contrast. So these axial images shown on the top here are taken, of course, in the same individual, but by adjusting the timing parameters in an MRI pulse sequence, we can obtain dramatically different image contrast, going from something that's relatively flat in contrast between white matter and gray matter to something wherein the white matter is actually gray and the gray matter is actually white, to something where the white matter is actually quite dark and barely perceptible except for its contrast against the gray matter. And then on this far right-hand image, you'll notice that the image contrast is relatively inverted compared to this left-hand image, where the gray matter is where the white matter is white and the gray matter is relatively gray. So MR, of course, has flexible image contrast. The question is, how do we manipulate the MR signal such that this image contrast becomes visible to us in the images we obtain? And what underlies that is that the fact that tissues have different T1 and T2 relaxation times. So MRI contrast arises from tissue differences in T1 and T2. And this is just a table of values at 1.5 Tesla. And we can see that gray matter and white matter, for example, have different T1 values and different T2 values. These are empirically measured. They're known or reasonably well known from empirical experiments, but they still undergo scrutiny and measurement using newer and more recent pulse sequence designs. And of course, there's biological variability. So these are not precise numbers, but kind of ballpark numbers. And what's interesting and good to notice, of course, is that there are differences between, say, white matter and gray matter. There are also big differences between, say, fat and muscle. And so I think it's important to remember and to understand sort of the range and some typical values for T1s and T2s of different tissues. And bracketing sort of both ends of the spectrum are things like fat, which has a short T1 and a kind of intermediate T2, and CSF, which has a quite long T1 and a relatively long T2 as well. And other tissue types tend to fall somewhere in between, except for things like kidney and muscle, which have amongst the shorter, or liver even, has amongst the shorter of the T2 time constants. So what about T1 and T2 image contrast? So as a consequence of the Bloch equations, which we described in the previous lecture, the underlying tissue T1, T2, and perhaps other tissue properties like proton density and diffusion, perfusion, and so forth, it turns out that the bulk magnetization vector is not of constant magnitude. That is, we can manipulate the bulk magnetization in different tissue types so that we can develop or manipulate the underlying image contrast. So by manipulating the magnitude of the bulk magnetization, we can generate the image contrast that gives us the conspicuity, that is the ability to see the thing that we're most interested in seeing. So these are different examples of the consequences of RF pulses and relaxation and the equations that describe the free precessional behavior of the bulk magnetization after the application of an RF pulse. So the previous lecture, these expressions were explained and described, although the derivation is not clear at this point in this course. And so what we're seeing here on this left-hand animation is the consequence of a 90-degree RF excitation pulse. So the bulk magnetization begins by pointing straight up along the z-axis. And after a 90-degree RF pulse, the spin, in this case the bulk magnetization, is forced to precess down into the transverse plane. And at this point in time, the RF pulse is turned off because the bulk magnetization has reached the position that we care about, that is, lying in the transverse plane. And that's a process of forced precession. The RF pulse forces the magnetization into that state. Now we enter, because the RF pulse is turned off, we enter into a period of free precession. And during a period of free precession, the bulk magnetization will return towards its equilibrium state according to the equations above. That is to say, the transverse magnetization continues to shrink and go towards zero, whereas the bulk magnetization returns on a path towards equilibrium, wherein the Z magnetization component is restored to its full equilibrium value, which is where the experiment started to begin with. So again, the 90-degree pulse tips down during forced precession, and free precession brings magnetization back into the equilibrium position. Now, with other RF pulses, we can tip more. So if we turn the RF pulse on for longer, we can tip farther. And in this case, the bulk magnetization tips past the transverse plane until it's partly what we call inverted. It has a negative Z component, if you will. And now, at the end of the RF pulse, at this time point here, we've stopped forcing the precession. We undergo free precession, and the magnetization recovers according to the expressions above, with the transverse magnetization decaying towards zero, and the bulk magnetization Z component recovering back towards its full equilibrium position. And so in this sense, we can see that the bulk magnetization is not a vector of constant magnitude. We can manipulate the bulk magnetization's magnitude through the process of the timing of different RF pulses. And the magnitude of the bulk magnetization will depend on that timing and also the tissue relaxation properties. So here in this last example, we see something really interesting. Let's see if I get back to this movie here. Pause it. Here we have the Z magnetization pointing straight up, and through the application of an RF pulse for a longer duration, we can actually invert the magnetization. And at this time point here, we turn off the RF pulse. We're no longer forcing the precession. And as a consequence of the above expressions, the magnetization will recover as follows. In this particular state right now, there is no transverse magnetization. The transverse magnetization is zero, and zero is just decaying as a function of T2, if you will. And so the bulk magnetization only has one option. It's going to recover along the Z-axis according to the first equation above. And in fact, it's going to recover until it reaches zero magnetization at this point here. And that means that after that 180 degree of forced precession, the magnetization with this time constant at this time point will in fact be zero. That is, there will be no measurable magnetization coming from that particular tissues. Other tissues will relax at different rates, and they might be visible, but this tissue will not. And if we wait long enough, then the magnetization continues to recover until it eventually reaches its equilibrium point again. So an MRI controlling the image contrast requires taking a snapshot, if you will, of the magnetization at just the right time. And at any point that was shown in any of these videos, in principle, we could choose to form an image. And choosing to form the image at the right time is what underlies image contrast formation in MR. So we begin by further describing T1 relaxation. And this refers to, as is no surprise, longitudinal, or what we also call spin lattice relaxation. This is typically on the order of tens of milliseconds to maybe hundreds of milliseconds. In fact, it could be thousands of milliseconds. And T1 is going to be long for small molecules like water, and it's going to be long for things like large molecules or proteins. And T1 is short for fats and intermediate-sized molecules. T1 is known to increase with increasing B0. That is, there is a field dependence on the relaxation property, T1 in particular. And T1 decreases with contrast agents. So there's no T1 lengthening contrast agents, but the addition of a contrast agent to an experiment will have the consequence of decreasing the underlying T1. And something that's really important to remember, especially in diagnostic radiology and just in understanding image contrast in MR, is that short T1s are bright on a T1 weighted image. And so if the image is is known to have been acquired with a T1 weighted image, and you see signals that are bright, you can then infer that that particular tissue has a short T1. And that can be important for informing you about the sort of molecular makeup of that particular tissue. It could, for example, be bright and similar in image signal intensity to fat, and you might understand that that tumor is a fatty lipoma, a fatty tumor, if you will, just by that simple association. So let's explore the signal response in a T1 weighted MRI using what we call an inversion recovery pulse sequence. So here we can see what happens to the MZ recovery after what we call an inversion pulse, or a 180 degree pulse, the pulse we were just looking at. So the magnetization would have initially at complete equilibrium have been associated with the M0 equilibrium value, but after a 180 degree RF pulse, all tissue types, whether it's white matter, gray matter, to CSF, which all have different T1 values, the bulk magnetization will be inverted to the same point, the same negative bulk magnetization. And the image that we would obtain at that point would be relatively flat in its image signal intensity, because all tissues have the same amount of Z magnetization, if you will. Now, the actual process of imaging requires generating transverse magnetization. MR is only sensitive to detecting the transverse magnetization, something we'll discuss later. But right now, just think about the fact that we have the same amount of Z magnetization, and whatever we need to do to generate now transverse magnetization will be taking the same amount of MZ magnetization for all tissue types. The point being, when we look at the image obtained at that point in time, at what we call an inversion time, a TI of 25 milliseconds, all tissues look relatively similar, whether it's white matter, gray matter, or CSF. The image contrast is relatively flat. Now, something interesting happens in MR images, and that is we only generate images that reflect the magnitude of the bulk magnetization. MRI only measures the magnitude of the magnetization. And that means even though this magnetization was actually inverted, we're imaging its absolute value, detecting its magnitude. And so the signal response curves actually follow these sort of rectified curves, if you will. So white matter appears in the sense to be decaying with longer and longer times until it hits some null point. That was the point at which the white matter magnetization would have recovered to the 0 point, if you will. We could get an image at this point, which we'll look at in just a second, and the magnetization then recovers just along its normal equilibrium path. So it's really a little bit of a trick, but important to remember that the magnitude signals we're looking at have this so-called signal bounce in them as well, and the consequence of that will be apparent in just a second. So here we chose an inversion time of 25 milliseconds, pretty short. Play the inversion pulse, and 25 milliseconds later we're generating an image. What happens if we wait, say, 200 milliseconds after the inversion pulse? Well, at this point in time, you can see that the relative signal contrast should be as follows. CSF signal should be relatively bright, and in fact, the CSF here seen in the ventricles is relatively bright. In this case, the gray matter signal intensity should in fact be a little bit brighter than the white matter signal intensity. And that's what we see. The white matter is actually relatively dark, the sort of skeleton shown here, whereas the gray matter, the cortical gray matter on the outside, is actually brighter. As we move forward, say, to this particular time point, this is where we see that inversion effect. So at this point, the white matter signal has reached its null point. It's been recovering, but we've waited long enough, in this case about 500 milliseconds before forming the image, that the white matter signal intensity is crossing that zero boundary, and in fact it appears to be very dark relative to, example, gray matter, which has a signal intensity that is, in this case, still bright. Or in fact, CSF, which, because it's been decaying so slowly, still maintains a relatively bright signal. And we can follow this out to, say, another time point here, and this becomes interesting because at this time point here, that CSF signal that was slowly recovering the whole time only does it now finally reach its null point. So if we wait 1,000 milliseconds after that inversion pulse, we can now see that the CSF signal is actually looking darker, or quite dark, and we've inverted the contrast, if you will, between white matter and gray matter, where white matter here appears quite bright and the cortical gray matter on the outside appears relatively dark. So we flipped the contrast between, say, this image with a shorter inversion time and the image with the longer inversion time. So you can see here, just through the application of a single RF pulse, an inversion, in this case an inversion pulse, and waiting different amounts of time, we can develop contrast that gives us the ability to see differences between tissue types with different contrasts. And clinically, that can be diagnostically valuable. So what about T2 relaxation or transverse relaxation, also referred to as spin-spin relaxation? It's the consequence of spins interacting with spins that in part gives rise to this relaxation effect, or a molecular interaction causing what we call spindephasing. Typically, T2 is on the order of tens of milliseconds, so it might be 100 or 200 milliseconds for some tissues like CSF. It tends to increase with molecular size and decrease with T2. That is, large molecules have a short T2, but something like fat has a short T2. Increasing molecular mobility actually increases T2. So consequently, liquids have long T2s, things like CSF or edema. And increasing molecular interactions actually decreases the T2. So solids actually have very short T2s. And that's why things like bone, ligament, tendon, meniscus, solid biological tissues tend to have very low MR signals. T2 is actually relatively independent of B0, and that's in distinction to T1, which had a B0 dependence, a field strength dependence. And remember that T2 is always less than T1. So when we're looking at T1 and T2 relaxation properties, T2 is always less than T1. And lastly, especially for diagnostic imaging, it's important to remember that long T2s are bright on a T2 weighted image. And you should see why when we look at some relaxation. So here we can examine what happens to the transverse magnetization during a T2 weighted MR experiment. So picture, if you will, that all of the MZ magnetization, all the bulk magnetization rather, points along MZ at equilibrium. But after the application of an RF pulse, specifically a 90-degree RF pulse, what we call a saturation pulse, the transverse magnetization will go from 0, which it is at pure equilibrium, to being fully the maximum available amount of transverse magnetization. Here we just indicate a normalized value of 1. So all tissues are tipped down into the transverse plane and have the same amount of transverse magnetization immediately after that RF pulse. And if we choose to quickly form an image, in this case reflected through what we call the echo time, the time to form the echo, the time to form the imaging information, we can see that image contrast is relatively flat. There's not as much contrast between different tissue types in this image. But if we wait longer and longer periods of time, something interesting happens, right? CSF has a long T2, so the CSF signal decays relatively slowly in the transverse plane, whereas white matter and gray matter have shorter, substantially shorter, but similar T2 relaxation time constants. In this case, the gray matter relaxes a little bit more slowly than white matter. So what does that mean? Well, after the saturation pulse is played, we can wait different amounts of time, allowing the magnetization to develop image contrast, if you will, and the image contrast will look fundamentally different at each of these time points because of these different relaxation properties for different tissue types. And so if we go out to intermediate times, we're waiting now 100 milliseconds after that saturation pulse has been played, we can see more distinct white matter, gray matter contrast. And in fact, we can see that the CSF signal stays quite bright. And if we wait until our longest time, at which point the echo time is, say, 235 milliseconds, so we've waited 235 milliseconds since the application of the saturation pulse, we can see that the CSF stays quite bright, which makes sense because our relaxation curve is decaying quite slowly. But white matter and gray matter show relatively dark signals everywhere because that signal has decayed quite a bit. And so what we should appreciate from this is that long T2s like CSF is bright on a T2 weighted, which is a long TE image. And that's exactly what we see here. A long T2 is bright on a T2 weighted image. So this diagram just is adapted from the Bushberg book and just relates both T1 and T2 and the underlying sort of molecular differences and how that changes the underlying T1 or T2 for different time constants. So long T1 or T2 or short T1 or T2. And we discussed this briefly before, but depending on the molecular motion, the molecular size, the molecular interactions, this will give us some insight as to whether or not a tissue will have a short T2 or a long T2 or a short T1, a long T1, a short T1, or in fact a long T1 again. And so this can be useful for kind of linking back to the tissue table of T1 and T2 relaxation time constants that I provided before, probably best and easiest to understand through an example. And so on the left-hand side here, we could use muscle as a proxy, and we know the T1 to be relatively long and the T2 to be relatively short, and it's consistent with having relatively slow molecular motion, large molecular size when you think of the sort of surrounding proteins and so forth, and the molecular interactions are relatively bound. This is a soft tissue being distinct, say, from a fluid. If we look at this intermediate case here of fat, we can identify that it has a short T1, so low T1, and a kind of intermediate T2, so it's on the rising edge of this T2 curve, if you will. And so fats, we understand, have intermediate molecular motion, intermediate sort of molecular size, they're sort of short CH2 groups, and intermediate molecular interactions relative to, say, other soft tissues or solids or fluids. And then if we move forward again and think about something like CSF, CSF is a good example of a tissue with a really long T1 as well as having a long T2. And that might make sense in the context of having relatively fast molecular motion. It's a fluid after all. Having small molecular size, very little in the way of protein. Mostly this is an ionic solution. And the molecular interactions are relatively free. And so this sounds like something that would describe CSF, and that's consistent with what we know and understand about CSF. So in addition to T1 and T2, we need to describe what we call T2 star relaxation. T2 star relaxation is the observed transverse relaxation time constant. And that's a little bit different than the T2 time constant for the following reasons. This represents spin-spin dephasing, which was what we understood T2 dephasing to depend upon, but it's combined with something that's irreversible. And that is to say, that this T2 spin-spin interaction is irreversible. Those losses of spin coherence or dephasing are not recoverable. So once we have generated transverse magnetization, it will irreversibly decay as a consequence of the relaxation equations that we showed previously, dependent on the tissue's underlying T2. But there are, in fact, reversible reasons for which the spins will also dephase, largely due to what we call intravoxel field inhomogeneity. And so if our B0 field is not perfect, and it never is, typically it's off by a few parts per million over what we call a diameter spherical volume of 40 to 50 centimeters. And that's equivalent to having a difference of about 640 hertz in Larmor frequency over a large diameter sphere of 40 to 50 centimeters. And that means that we're off by about 1.5 microtesla if that's a 1.5 Tesla scanner. And it might seem like that's a really small amount to be off and that this is really a high precision instrument, and I wouldn't disagree, but this level of imperfection actually has a consequence on image quality and in fact image contrast. We could also have so-called susceptibility differences that give rise to intravoxel field inhomogeneity. So the magnetic susceptibility of tissues is not uniform. It can differ at sort of the micro scale or the macro scale, and it will induce small field perturbations, and if the field is not perfect, you'll get so-called dephasing. That is, spins will fall out of coherence with one another. These sources of intravoxel field inhomogeneity, though, they're reversible. That is to say, they're caused by a field, and if we can impart an equal and opposite field, then we can reverse these effects. So, for example, they can be rephased with a spin echo, a sequence that we haven't talked about quite yet, but they cannot be rephased with a gradient echo. And that may not be obvious yet, but the reason for that is that the spin echo uses what we call a refocusing pulse, which sort of enables reversing these sources of spin dephasing. A good thing to remember is that T2 star is always less than T2, so these are additional sources of off resonance that cause additional signal dephasing, additional signal losses, so the time constants are even shorter than they are for T2. This is one way to understand the relationship between T2 star and T2. So 1 over T2 star is equal to 1 over T2 plus gamma times some delta B0. And you can look at the units of this to understand that it looks like 1 over a time. These are the irreversible losses, but these are the reversible losses. So in the case that there is no delta B0, there's no B0 gradient within your pixel, then the T2 star is in fact equivalent to the T2. But unfortunately, it's always the case that there's some delta B0 leading to some reversible losses in our spin system. And sometimes this is referred to as 1 over the T2 prime. So we keep talking about spin dephasing, and I want to give a more coherent or clear example of what we mean by comparing both T2 relaxation and T2 star relaxation. So let's set up the scene here. On the left-hand side, we have so-called T2 decay. We have a system of spins, a bunch of spins. They all have slightly different phase, right? There's some dephasing already. And these are spins that wholly occupy a voxel that we care about. On the right-hand side, we have a similar situation. It'll be a little bit different, but this is going to represent T2 star decay. And so here we get signal loss, but that signal loss comes from spin-spin interaction that we don't easily depict. If these spins are set into motion to precess, you'll see that their transverse magnitude is decaying as a consequence of spin-spin interaction, and that's the conventional T2 decay. And as the spins are swinging past our coil, we are picking up a sinusoidal oscillation at the Larmor frequency, but its amplitude is decaying because the magnitude of the transverse magnetization is decaying as a consequence of T2 relaxation and spin-spin interaction. In the presence of having spin dephasing due to intravoxel field inhomogeneity, there's going to be signal loss from spin-spin interaction. This is the irreversible part, and off-resonance dephasing, which leads to T2 star. And that off-resonance dephasing is in fact reversible through a process that we'll describe in the spin echo component of this lecture. So here the distinction is that the spins are going to precess, generate a transverse magnetization that we can detect with a nearby coil, but the spins are not only decreasing in magnitude, they're falling out of phase with one another. And as the spins fall out of phase with one another, let's go to this. Sorry, in just a second we'll advance to this video on the right-hand side. As these spins are precessing, they're also falling out of phase with one another, and as they fall out of phase to be uniformly out of phase, they no longer produce a detectable NMR signal because there's no net flux through the coil here. And so the signal still precesses and oscillates at the Larmor frequency, but it decays very quickly as a consequence of spin-spin interaction as well as spin dephasing. So we see signal loss from spin dephasing and T2 or T2 star. And so remember again that T2 star is always less than T2, and so we could map out what happens to white matter, for example, were we to measure the available signal due to T2 decay and T2 star decay as a function of time. In this case, again, the magnetization would start off at the equilibrium value of 0. If we play a 90-degree pulse, then we have transverse magnetization that's fully occupied, or if you will, so 1 on an arbitrary unit scale, and both those signals are going to decay, but the T2 star decay signal is going to occur more quickly because T2 star is always less than T2. So here's a set of T2 star weighted gradient echo images. Gradient echoes are one of the ways in which we form MR images. And we can see here that what we're doing is extending the echo time. This is the time it takes us to actually form the echo signal. We're just making that longer and longer and longer. And that just means that having generated some transverse magnetization, we can form the image very quickly with a short echo time, or we can wait quite a bit of time before forming the echo, 50 milliseconds in this case. And you can see that just by changing the echo time, the image contrast changes quite a bit. Here we understand or notice that the synovial fluid has a long T2, so about 1200 milliseconds, which is different than, say, subcutaneous fat or muscle. And the muscle signal here is bright. All tissues are relatively bright with a very short echo time, but the muscle signal is obviously decaying pretty quickly as a function of extended echo times. The fat signal is decaying a little bit more slowly, has a longer T2, or T2 star, in fact, and the synovial fluid has the longest signal. So you can see the synovial fluid here persisting the longest. Thank you.